Hey guys, and welcome back to section 4, and we're going to be looking at expectation maximization and what it is. This is a really neat algorithm. It is quite probabilistic though, so those who aren't up to scratch with probability might find this video quite intense and not really be able to follow very well. But don't worry, because our implementation doesn't really require us to understand the algorithm, the implementations that well. It's more just what's going on at a high level. So in this section, we're going to take a look at what is EM and when do we choose it. We're going to then be implementing expectation maximization, and then we'll have a discussion on expectation maximization. So when to choose expectation maximization, video 4.1. And in this video, we're going to take a look at what is EM and when do we choose it. So what is expectation maximization? So it's a method that can be used to find model parameters, and it achieves similar parameters to maximum likelihood estimation. Don't worry if you don't know what that is. If you do, that's great, it's perfectly fine. But it obtains the results in an iterative manner. So the likelihood is basically the probability of the data given some parameters. So if I said, if you're doing heads or tails, and the parameter is generally going to be 0.5, which is the probability, which is a standard binomial distribution. So if we had heads then tails, then heads then tails, then heads then tails, then heads then tails, conditioned on the parameter A being 0.5, then that likelihood is going to be very, very high. And it can be shown that the maximum likelihood parameter, the parameter that obtains the maximum likelihood for a binomial distribution, is 0.5. What you effectively do is it's the argument over this likelihood function. So basically maximum likelihood is just picking the parameter of the distribution that maximizes this, the likelihood. So often this is just solved analytically, argmax, you just differentiate it and find the largest value. Basically, that's just like school calculus. So rather than trying to maximize it analytically, expectation maximization proposes a parameter and then iteratively tries to maximize the expectation. So you think of it a bit like when we were doing training linear regression in our very first product. We could have solved it analytically, but we chose to use gradient descent, which increased so its real strength comes in when we have a multimodal distribution and hidden variables. So if you've got two distributions really that make up one, to use kind of layman's terms, that's when it comes into play, because this is when maximum likelihood will not obtain your true value. So if you've got two distributions that are similar height, MLE will just pick one of them, and it won't give you any intuition as to what's near it, what else is around. It will just say this is the best, when actually, there might be 5 other parameters that pretty much give exactly the same result. So it's best if we probably do a short example. So going back to the coin example, so if you assume you've got 2 visually identical coins, and the probability of a heads is A1 and A2. So they're biased coins, they're not going to be heads or tails every time. And then let's say we close our eyes, we pick up a coin and we flip it 5 times. And the first time we get this series of data. We then put it back down, close our eyes again, pick up a coin, it might be the same one, it might be different, we don't know. And then we get this data. And then we do the same again, and we get this data. Now, as you can probably see, being humans, we're pretty smart. We can see that this data and this data are very similar, and this one is completely different. So you'd say that this one's probably got quite a high probability of obtaining zeros, so we'll expect the A value for this distribution to be low, and the A value, or coefficient, for this value to be high. So then, basically, what expectation maximization will try and do is it will obtain these 2 parameters for the different distributions. And then effectively you can kind of see how we can perform clustering in that sense, because you can say, well, this distribution has this parameter and this distribution has the other parameter, and if it falls in there, it's likely to be, we can model it using these coefficients and these values. So what we do is we pick two initial guesses at the values of A1 and A2, and then for each set of trials, so for each one of these, we compute the likelihood for the trials. So this would just be half times the number of trues, 1 minus half the number of falses. And then for each one of those, we try and calculate their values which maximize the expectation of. So for this, we then want to maximize that for all of the data, and that will then increment our values of A1 and A2 towards their true value. And that's effectively what EM does. That's all the detail I'm going to go into it now, because this isn't a maths course, this is like practical machine learning. But you need to just think of it like that. It's based on probability and maximizing the likelihood of something happen, and you do it iteratively, and it's able to obtain two values. So just to recap, the reason maximum likelihood would be no good here is because, well, there's two values really, and there's evidently two distributions. So maximum likelihood kind of falls down here and can't really get anywhere. But yeah, that's EM. Don't worry too much if you don't get it. Hopefully it'll become a little bit clearer on a high level what's going on when we do the implementation. But I do encourage you to read up a little bit more. It is quite a hard one to get your head around,